Biconditional statements. When a conditional and its converse are true, you can combine them as a true biconditional. So the prefix in biconditional, bi, meaning two. This is the statement you get by connecting the conditional and its converse with the word and. You can write a biconditional more concisely, however, by joining the two parts of each conditional with the phrase if and only if. A biconditional statement is a statement that can be written in the form P if and only if Q. And this is the symbol for that. P if and only if Q means two things. That P implies Q, if P then Q, and the converse, if Q then P. So it's an abbreviated way of conveying that there are two ideas at once. And we have options. We can write out P if and only if Q in words. We can abbreviate if and only if with this funny way of spelling if, IFF. This means if and only if. And the double arrows also mean if and only if. In geometry, biconditional statements are useful to define various figures. A good definition uses clearly understood terms, is precise, and is reversible. So determining the truth value of a conditional statement, or for a biconditional statement. A biconditional statement is true if both the conditional statement and the converse that they contain are true. If any one of those are false, the biconditional is false. So we can write any biconditional with two ideas, the conditional and the converse of that. An angle is obtuse if and only if its measure is greater than 90 degrees and less than 180 degrees. Well, this sentence is a biconditional statement. It has if and only if, and it contains two ideas. One idea that it contains is, if an angle is obtuse, then its measure is greater than 90 degrees. So how do we take a biconditional and write a conditional? We have the word if, as we did here. If an angle is obtuse was added to an angle is obtuse. Now, since it's a conditional, it doesn't have if and only if. We've taken if and only if out, and we've added the word then, because every conditional is an if-then statement. So one idea contained in this biconditional is, if an angle is obtuse, then its measure is greater than 90 and less than 180. This biconditional contained two ideas. It also contains the converse of this conditional. So take a moment and write the converse of this conditional statement. You should have, if an angle's measure is greater than 90 and less than 180, it is obtuse. After all, the converse of a conditional is when you switch the hypothesis and conclusion. This one sentence, this biconditional sentence, contains both of these ideas. Next, a solution is neutral if and only if its pH is 7. So the double arrows. So this is a biconditional statement, meaning it contains two ideas, a conditional and a converse of the conditional. How do we convert a biconditional statement into its two conditionals? We add if and then to it. If starts the sentence. So if a solution is neutral, what? Then its pH is 7. This is one of the two conditional statements that this biconditional contains. What's the other one? Well, it's the converse of this conditional that we've derived. So write the converse. You can pause and write it and check. You should have, if a solution's pH is 7, then it is neutral. You should not be writing if its pH is 7 in this sentence, because what is it? Every sentence should be able to stand on its own, so don't use a pronoun. The subject of this was a solution. The pronoun was used because it was already referred to in the subject of the beginning of the sentence. So if a solution's pH is 7, then it is neutral. You can use the pronoun since you've referred to it. Continuing, write the converse and a biconditional statement. So two things to do here. We'll start here. If 5x minus 8 is 37, then x is 9. Well, write the converse, and then combine them into a biconditional. You can pause and check back. Okay, let's check. The converse, if x is 9, then 5x minus 8 is 37, is the converse because we switched the hypothesis and conclusion from the conditional above it. How do we combine them into a biconditional? Well, biconditionals don't start with the word if, and they don't have the word then in them. You start with a subject, and they have if and only if. So we have an option. We can say 5x minus 8 equals 37. What? If and only if x is 9. It would be just as correct to say x is 9 if and only if 5x minus 8 is 37. You can use if and only if. You can use the double arrows. This is probably the most efficient. So this is the biconditional. This sentence contains both of the ideas we've written above. Let's get the converse and the biconditional of this one. If two angles have the same measure, then they are congruent. What's the converse? Switch the hypothesis with the conclusion. And then write a biconditional. You can pause here and do both of those things, and then check back. So if you switch the hypothesis and conclusion, you get the converse. If two angles are congruent, then they have the same measure. How do you write a biconditional? Biconditionals don't have the word if in them, and they don't have the word then. We combine the two ideas by starting off with the subject. Two angles are congruent if and only if they have the same measure. Did you write two angles have the same measure if and only if they are congruent? That is just the same. So in this case, if and only if means the same as the double arrows, means the same as spelling it out if and only if. So a biconditional statement is efficient. It contains two ideas. It combines them into one. All right, let's determine if the given biconditional is true. If false, give a counterexample. Just on the prior page, it was established that a biconditional is true if both the ideas it contains are true. That is the conditional and its converse. If any one of those two is false, the biconditional is false. So a rectangle has side lengths 12 centimeters and 25 centimeters if and only if its area is 300 square centimeters. Are the two ideas contained in the statement true? Well, would you please write the conditional statement that this contains and its converse. You can evaluate the truth value of both and check back and see how you did. You should have written one conditional statement. If a rectangle has side lengths 12 and 25 centimeters, then its area is 300 square centimeters. Is that a true or false statement? Well, if the lengths are 12 and 25, you find the area by multiplying those. And 12 times 25 is, in fact, 300. So anytime you have a triangle with side lengths 12 and 25, it will be 300 square centimeters. This is a true statement. What determines if the biconditional is true? If the converse of this is also true. Did you write the converse? If a rectangle's area is 300 square centimeters, then it has side lengths of 12 centimeters and 25 centimeters. Oh, that's extra. Is the converse true? Imagine an area of 300 square centimeters. Is it possible that they're only 12 and 25 centimeter lengths? No. The conclusion could be that they could be 15 and 20 centimeters. So this is false because not every 300 square centimeter rectangle has dimensions of 12 and 25. So this is false. Our objective is to determine if the given biconditional is true. Why is it false? Because one of the ideas it contains are false. So this is a biconditional statement, but it happens to be a false one. a natural number n is odd if and only if n squared is odd. Natural numbers are essentially the counting numbers, 1, 2, 3, 4, 5, whole numbers, no fractions or decimals or not pi, not the square root of 5. The numbers we use to count. So think of a number, a whole number that is odd. And if we square it, is the result odd? Well, I got a little ahead of it. Let's see if the two ideas that this contains are true or false. Write a conditional and its converse that this idea contains. You can try to write it and then check back. All right, one conditional statement. If a natural number n is odd, then n squared is odd. The converse of that, if a natural number n squared is odd, then n is odd. Were any of these true? So a natural number, an odd natural number could be 3. Well, if we square 3, is that odd? 3 squared is 9. The next odd number I think of is 5. When we square 5, we get 25. That's also odd. Is there a situation where we square an odd number and we don't get an odd result? In every case, that seems to be true. This is a true statement. Now, our objective is to determine if this biconditional is true. The converse has to be true as well. So this is like going backwards. If a perfect square is odd, is its square root odd? Well, we just talked about 9. 9 is a perfect square. Its square root is 3. That's odd. 25 is a perfect square. Its square root is 5. Also odd. 81 is a perfect square. That is odd. Its square root is odd. This is also true. So what does that mean? It means that this biconditional statement is also true. When all the ideas, in the case of a biconditional, when both of the ideas are true, the biconditional is true. If every one of them is false, then the biconditional is false. And we need to write definitions very clearly and exactly. And a biconditional is excellent in math to describe things, especially in geometry when we're talking about geometric figures. So let's define these terms using a biconditional. A pentagon is a 5-sided polygon. Can we convert this into, add more information to make this a biconditional? Well, we can say a figure is a pentagon if and only if it's a 5-sided polygon. What this means is every pentagon is a 5-sided polygon. At the same time, anytime you're looking at a 5-sided polygon, you can only call it a pentagon and nothing else. It defines it exactly and doesn't leave room for it to be any other figure. Let's write a right angle measures 90 degrees as a biconditional. So let's define right angle. Maybe something like a figure is a right angle if and only if it measures 90 degrees. Or an angle is a right angle if and only if it measures 90 degrees. So biconditional statements contain two ideas, a conditional and its converse. For them to be true, for a biconditional to be true, both those ideas have to be true.